Hi everyone. In this video, we're going to talk about disjunctions. So this will continue our conversation about probability. In the last video, I mentioned that disjunctions involve probability questions with the word or. For example, what's the probability of rolling a sum of 3 or 7 when rolling two fair six-sided dice? So problems like these are called disjunctions. And so we are going to answer this question without writing out the entire sample space of rolling two six-sided dice because we already did that in the previous video. If you'd like to, of course, you are welcome to, but I'm going to just remind us how many total options there are. So there should be 36 total equally likely outcomes. Okay, that's why we're able to answer this question because we can use theoretical probability to answer this question. So we already know that there's 36 total outcomes. Okay, so let's find the probability of each of these things. What's the probability of rolling a sum of 3? Well, let's count how many different ways we can get a sum of 3. We can have the combination 2, 1, or we can have the combination 1, 2. So those are the two ways that we could get a sum of 3. So then the probability is 2 out of 36. And what about a sum of 7? So the probability of rolling a sum of 7, well, how many outcomes are there to get a 7? We could have 1, 2, I'm sorry, not 1, 2, 1, 6. We could have 2, 5. We could have 3, 4. Notice I'm trying to go in order. That's why I started with 1. I did a bad job here. I didn't start with 1 here because I knew that there was only 2 answers. But I should really have listed this one first so that it was systematically. So I'm going in order here. 1, 2, 2, 3. The next one would be 4, 3, 5, 2, and 6, 1. All right, so there's all the possible outcomes for rolling a sum of 7. And 1, 2, 3, 4, 5, 6, we get 6 out of 36. So if we want to know the probability that either of those two things happen, or both, but you can't roll both a 3 and a 7. So we're really talking about the probability of a sum of 3 or 7. This is a disjunction. You would add up how many total ways can both of those things happen. Can either one of those things happen or both? So 1, 2, 3, 4, 5, 6, 7, 8. There are 8 total ways that you could roll a sum of 3 or a sum of 7. And notice that there's actually no overlap here. So no combination shows up down here because you can't roll a sum of 3 and a sum of 7 at the same time. But what if you could? What if there are other types of examples where there would be some overlap, where you might have the same element repeated? So that's what we're going to do next. We're going to do an example like that next. And then I'm going to draw some Venn diagrams to help us understand what's going on. To prepare you for what we're about to see, the Venn diagram for these two sets, if I use the same colors, if this is the probability of rolling a sum of 3 right here, and we knew that there were only 2 options in this set, then the probability of rolling a sum of 7 would be next to it, not touching it. They wouldn't be overlapping. Oops, there are six options for rolling a 7. There would be no overlap for that Venn diagram because they don't have anything in common, and that's why the total here adds up to 8. If they had something in common, we would draw a Venn diagram like this, and we would put whatever they had in common in the middle. And that's what we're about to do. Okay, so I'm going to erase all this, and we're going to put a different example problem up. All right, so this example is going to be about a class of students and what kind of pets they own. So let's say out of 24 students, 15 own a dog. 7 own a cat. And 5 do not have any pets. Okay, so what's the probability that somebody owns a dog or a cat? What is the probability of a student owning a dog or a cat? All right, so that's what we're going to answer. So again, this is a disjunction because the question is about what's the probability of owning a dog or a cat. Okay. So first, I'm going to draw a Venn diagram to wrap my mind around what's happening with all of these numbers. All right, so let's say that these are the people who own dogs. These are the people who own cats. And the total should add up to 24 students. So this whole, like if I put a box around here, sometimes people do that. This whole thing should add up to 24. No, I just put the total in the top. All right, so let's see. So how many people own dogs? It says 15 students own dogs, but do you agree some students could own both a cat and a dog? So then if we were sitting in a class of 24 students and I said, raise your hand if you own a dog, and you put your hand up because you own a dog, and then I said, everybody put your hands down. Now raise your hand if you own a cat. Well, if I own both, my hand will go up again. And so those students who might own both would be counted in both of these numbers, 15 students who own a dog and 7 students who own a cat. All right, so keep that in mind. So the 15 students who own a dog, that's not just this part of the circle, that's the whole circle, which might include some people who own a cat. So I'm just going to put the 15 up here so that I don't confuse myself with it's not just this part. If I wrote it inside here, I might be confused of if it's the whole circle or if it's just this part of the circle, in other words. Okay, the cats I'm going to put in red for the same reason. I'm going to put the number of people who own a cat up here, so like near the cat circle. So there are 7. Okay, and then 5 don't own any, so neither a dog or a cat. So we can put those 5 people, you know, like outside of the circle somewhere. Maybe we'll put the 24 on the outside so we know that the whole square should add up to 24. But there are 5 students who don't own either a dog or a cat, so they won't be in the circle. All right, so the total is 24 of the whole of everything in here should be 24. Okay, so that means the people just inside this Venn diagram, if you subtract 24 minus 5, we get 19. So just in the Venn diagram, there should be 19 people. So now that we know that, we can answer the question, what's the probability if somebody owns a dog or a cat? There's 19 people who must own a dog or a cat. And this or is an inclusive or, so it also includes people who might own both. So in other words, it means what's the probability of someone owning a dog or a cat or both? Okay, so we could put the answer, but I want to keep going so that we really unpack everything that's happening here in case you were asked a different question, which I'll show you in a minute, but let's put the answer. Probability of owning dog or cat is 19 out of 24 because there's 24 total students. And we could write that as a decimal. So you could divide that and you could write that as it's roughly 79% or 0.79 if you want the decimal, or 79% if you want the percentage. Okay. All right, so let's unpack what's happening here, because while there are 19 people in this whole Venn diagram, if you add 15 plus 7, you get a number that's bigger than 19, right? All right, so let's check. So if you do 15 plus 7, you get 22. But there's supposed to be 19 people here. So why is it that there are more people there when I add these two numbers than the number of people we know should be in there? All right, so let's show over here. If we do 15 plus 7, we get 22. This is more than 19. Okay. And why is that? Because we have counted some people twice. So I expected this to be more. I expected when we added these numbers, I expected that to be more than 19 because some people are counted twice right in the middle. Some people are counted right here. How many of them are counted right there? It should be however many excess people we have compared to what we know we should have. So if we have 22 people there, 22 minus 19 is 3. So that means there should be 3 people right here in the middle. So in other words, 3 people must own both a dog and a cat. And if we use that logic, we can also figure out how many people own only a dog and how many people own only a cat. So if 3 people own both and 15 people have dogs, then 12 people have only a dog. Likewise, if 7 people own a cat and 3 people own both a dog and a cat, then that means only 4 people own just a cat without also owning a dog. Again, I found these by doing 7 minus 3 and got 4, and 15 minus 3 and got 12. So now, if you add these together, which is why I put the numbers above the circles to help us see what's happening, these are the number of people who only own a dog. So there's 12 people who, let's put probability of dog or cat again, equals the probability of only dog plus, I'll put them all in their respective colors, the probability of only cat plus, in green, the probability of both. Okay, so here we go. Only a dog is 12 out of 24. Only a cat is 4. And the ones who own both is 3. And if you add all of these up, 12 plus 4 is 16, and 16 plus 3 is 19. So again, you see we get 19 out of 24. So that's one connection there. There's lots of different ways that you can think about these problems. That's why the Venn diagram tends to be helpful. It's a helpful visual. So you can just figure out, if you want to know how many people own either this set or this set, you can just take away the people who don't have either thing from the total amount of people. That will give you everything that's in this Venn diagram. That should be the same if you knew how many people were only in this part of the circle, not including the middle, plus the people in the middle, plus the people only in this part of the circle. There's one more way to do this problem, and so I'm gonna show that to you. I'm gonna erase some of this and show you the formal mathematical way to think about disjunctions. Okay, so let's put it right here. So another way to think about this problem, and we should still get 19 out of 24 as the answer, is to figure out how many people are in the intersection. This is called the intersection because it's the part of the Venn diagram that shows what's in common between the two sets. So we call that the intersection. All right, so if you can figure out the intersection, which we knew already to be 3, then the probability, I'm going to do some abbreviating here. I'm just going to call this D for dog and C for cat. The probability of D or C would be the probability of owning a dog, which is this whole circle, plus the probability of owning a cat, which is this whole circle, minus the probability of owning both, so a dog and a cat. Okay, so let me explain how I'm thinking about this. If I take all of the people in here, which is 15 people, so it's not only the people who own only dogs, that would be 12. It's everybody who owns a dog, including people who also might own a cat. Okay, plus if I add to that the people who own a cat, and when you say it like that, it means every person who has a cat, even if they also have a dog. So that would be 7. And then you subtract off the people who we know own both. This should still give you 19. So if we subtract off 3, all of these would be over 24 as well. So let's fix that because we're talking about probabilities here. Okay. Which doesn't matter. You can just put over 24 at the end. You're still doing the same reasoning. Okay, so let's see. 15 plus 7 is 22. 22 minus 3 is 19. So you still get 19 out of 24. So this is yet another way to think about this problem. Why does this method work? And this is the key formula that I want you to understand from this lesson. This works because if you take all the people who own a dog, add that to all the people who own a cat, you have just counted some people twice. You've counted the people who own a dog and a cat in this set, and then you counted the people who own a dog and a cat again in this set. And we only wanted to count them once. So then if you just subtract the intersection, what both sets have in common, then you'll make sure you only count those 3 students once. Because right now, those same 3 students are counted in the 15, and those same 3 students are being counted in the 7. But we only wanted to count them once. So we'll just subtract it to make sure that we're not double counting the same people. Okay, so I'm going to write this in general using some more formula math notation. But if you understood this concept, the notation means the same thing. It's just learning how to write it mathematically. Okay, so in general, if you have 2 sets, and let me just erase this, and I'll just start the general notes for us. All right, so in general, so if you have let's assume you have 2 sets. And we'll call them A and B, just for simplicity. I want to show you all of the different concepts that you could be asked about these kinds of problems and the different notations. So first, the probability of A or B, which is the example that we just did, that's represented by what's called a union symbol. It looks like a U. This is called a union. Again, this is just notation. So if you're more comfortable writing it this way, then go for it. But you're going to see some problems that also involve that symbol. And they mean the same thing. Okay, so I just wanted to make sure that you've seen this notation. The probability of A and B, which was what I said, the intersection, I called that the intersection of the 2 Venn diagrams, that we write that with an intersection symbol, which is the same symbol, but it's upside down. So it's like an upside down capital U. That means and then this is called an intersection. Okay, so this is called A intersect B, the intersection of A and B. Okay, and so as long as you understand those 2 things, I'm going to write the same exact thing we just wrote before. We wrote the probability of A or B is the probability of A plus the probability of B minus whatever we just might have double counted that's in both. So we just did that with the dogs and the cats. So I'm going to write this using the notation now that means the same thing. So you could write this as A union B, which means A or B, equals the probability of A plus the probability of B minus the probability of A and B, because that symbol means the same thing as and. Okay, let's show all of these ideas in a Venn diagram. So let's say you have a Venn diagram of two sets. Okay, we'll call one set A, the other set B. So here's set A, and then we'll put B in red. Here's set B. So what I'll do is I'll shade this and then I'll kind of erase it, but in your notes you should have a bunch of different examples, so don't erase it in your notes. Put all of this in a separate. So like in my notes, I'm going to have a bunch of shaded bubbles like this. So you should do each one. Okay, so first of all, here's the probability of A union B, which is the or A union B. It would look like all of this. That's A union B. Maybe I'll put 4 up here so that I don't have to erase, so that you can see all of them. Hold on, let me give myself a little bit more room. Okay, so let's put it over here. So we'll put A union B there, and then we'll put A intersect B here, and then we'll do 2 other examples here, and then I'll erase if I have to. Okay, so here we go. Let's try this one more time. Here's A, and then here's B. And you can use colors in your notes too. Highly recommend it. Okay, so the union, A or B, probability of A union B, is everything. It's what's in A and what's in B and what's in the middle. So it's the whole Venn diagram. The probability of A and B is only what they have in common. So it's only that middle part of your Venn diagram. It's only the intersection of the two sets, if you will. Okay, then we also need to know the probability of just A, because you see that happens here. So the probability of, and I shouldn't say just, it's the probability of A. So the probability of A is everything that's in A, including some stuff that might be in B. And over here, the probability of B is everything that's in A, that's in B, including stuff that might be in A. Woo, just keeping you on your toes, making sure that you're really understanding what I'm saying. Okay, so there's 2 more sets that I wanted you to see that I'm gonna just erase and put them on here somewhere so that you have them in your notes. And that would be the probability of only A, which I would have to write out. So add 2 more circles to your notes. I'm just gonna change these 2 right here. The probability of only A would mean only the things in A, not the things that are in both A and B. And over here, the probability of only B would be only the things in B, not the things that are in both. Okay, so I wanted to make sure you have all 6 of those in your notes. So here's 4. The other 2 that we just had were what you see here, the probability of A, which includes stuff that might also be in B. It's everything that's in set A. And also the probability of B, which includes stuff that might also be in A. It's everything that's in B, this whole circle. So I wanted to show you this because sometimes when students use formulas like this, they tend to figure out what's in only A, and then they use that number here. But this formula doesn't say only A. It says A, which means everything in A, which could include elements that are in set B, which is why you subtract, because you would be adding things that are in the intersection twice, and you only want to add that once. You don't want to double count. Okay, so those are disjunctions. Some practice problems in this area will help you to understand how to set these diagrams up for different kinds of problems in different contexts. But I wanted to close with reminding us of the two examples we did in this video. So the first one we did was about dice, and we did what's the probability of rolling a 3 or a 7. So I just wanted to remind you that for that example, the probability of a 3 or a 7, it should be what's in both circles, like all the Venn diagram. But those two sets didn't have anything in common, so those sets look like this. The probability of rolling a 3 or the probability of rolling a 7, they didn't have anything in common. There was no overlap. So this type of situation has a special word. They are called mutually exclusive events because they exclude each other. They mutually exclude each other. Set A has nothing from set B in it, and set B has nothing from set A in it. So they're mutually, excluding one another. Unlike the second problem we did about the dogs and the cats, those had something in common, so the Venn diagram would have looked something like that. So that's why in the first example, we didn't have to subtract anything because they had nothing in common. But in the second example, we did have to subtract the intersection because that's what they had in common. All right, so mutually exclusive events have no intersection. In other words, they have nothing in common. So you can always use this formula for any of these types of problems. You can always use it. The difference is if you have some mutually exclusive events, then you might just be subtracting 0 because there might not be anything in common. So in general, I suggest you get used to these formulas. They both mean the same thing. One's written in English, one is using the new math notation. And you can always use them even if you have mutually exclusive events because you would just be subtracting 0, which won't change your answer. Okay, in our next video, we're going to still continue talking about probability questions, and we're going to get into some more complex probability questions that involve conditional probabilities.